Welcome back, everyone. This is explain-04 of part 1 of my video series. I wish I had watched this video when I started learning about AI. Here's the URL for the repo. Now let's get started. So, what is the derivative of a matrix? Remember, matrix is a 2D tensor, and it also has a grad field. Tensor.grad, it has to carry along with it the partial gradient. This means that the grad field has to be the exact same shape as the original matrix. Okay. So, what are we doing? We need to calculate the gradient, and that means for each of the left hand sub I sub j, and for the right hand as well, sub I sub j, we need to calculate the gradient for each of these values. Now, thankfully, each of these values are composed by just simple multiply and add. So I think there's going to be a good intuition here as to how this is actually going to work. Let me say it in a different way. Think of a matrix multiply as being similar to a regular multiply. It isn't, but just assume that it is the case. Okay. And the reason why that intuition will hold is because the matrix multiply is simply a collection of multiply and add operations. Here's a hint. For C equals left hand times right hand, DC, the left hand, has to involve RH. Right? And DC, the right hand, has to involve the LH. It will be real nice if differentiating the matrix multiplies work the same way. So if A's shape is 3 rows and 4 columns, and B's shape is 4 rows and 2 columns, if we do C equals A matrix multiply B, the resulting matrix multiply is going to be a 3 by 2 matrix. So here is each cell of the matrix multiply written out. Okay, so here are each of the cells, C0, C1, C10, C11, C20, C21. Okay. The A bracket 0, colon is a Python and PyTorch array access notation. It means row 0 of A, because the column accessor is colon, which means all of the elements for that column. Similarly, for B colon 0, it means column 0 of B for the same reason. Just as a reminder, matrix multiply can be thought of as doing a repeated number of dot products. If the output matrix is of shape R by C, in this example of 3, 2, or 3 by 2, we need to do a total of 6 dot products. For each row of the left-hand matrix, do a dot product with each column of the right-hand matrix. Row, column, row, column, row, column. I wrote out each of the 6 dot products for each of the 6 cells in C. Okay. Reminder, when we're doing the backward operation, it comes after the forward operation. In other words, for the forward operation, we have the left hand, we have the right hand, and we do the matrix multiply, resulting in the output matrix C. In the backward operation, we have C dot grad, which has to have the same shape as C, which is 3 by 2. And we also have C. We also have A and B, and we want to calculate A dot grad and B dot grad. So how do we go about it? Let's take a look at cell C00 and cell C01. Okay. Notice that the value A00 only occurs at these 2 locations. So in order to, in other words, the partial derivative a00 must involve c dot grad, but only from those positions c00 and c01. So in order to calculate a dot grad at position 00, we look at the expression for cells c00 and c01. Okay. dc dA of cells of cells 00 must involve b00 and b01. Why? Because when you calculate dc of dA sub 00 from c00 equals a00 times b00 plus a01 times b10 plus a02 times b20 plus a03 times b30, so on and so forth, and c01 equals a00 times b01 plus a01 times b11 plus a02 times b21 plus a03 times b31. Little typo there. The a00 goes to 1. So you're left with 1 times b00 plus 1 times b01. Repeat. If you're calculating dc with respect to d cell a00, right, it has to involve b00 and b01. Why? Because cells a00 goes to 1. Okay. What does that mean? It means that the 1 in 1 times b00 plus 1 times b01 is actually the partial gradient of c, where b00 and b01 contribute to the value of c. Which means that dc dA sub 00 is going to be dc00 times b00 plus dc01 times b01. In other words, c dot grad at position 00 times b at cell 00 and c dot grad at position 0 comma 1 times b at position 0 comma 1. Going by the same pattern, you can write out the partial derivative of c with respect to each position of a. In other words, you're calculating dc dA for all coordinates in a. And soon you realize the following. The products actually look like the matrix multiply operation, and c dot grad and b are involved. But there's a twist. Using c dot grad and b, there's only one way to arrive at the matrix with the same shape as A, and that is to do c dot grad matrix multiply B transpose. Similarly, when you write out the partial derivative of dc with respect to dB, you also realize the following. It is also a matrix multiply involving A and C dot grad. Using those two matrices, there's only one way to get matrix with the same shape as B, and that is to do A transpose matrix multiply C grad. And that is why I chose the shapes of A and B specially. If you had used square matrices, you might have wound up picking the wrong solution. Okay. In summation, the matrix multiply is a lot like normal multiply, except they're not commutative unless they're square matrices. And they are associative as long as each pairwise matrix multiply operation is also legal. So that, in essence, is how to calculate the partial derivative of a matrix times matrix or a matrix times vector. You'll probably want to read through these notes very carefully. I'm fond of saying you'll need to squint at the notes until you're convinced. Now on to part 5. So this ends part section 0 or explains dash 04 of part 1 of my video series. Thank you very much.